morning and welcome to lecture number 4. As customary, let's start with a quick summary of what are the some of the key points that we mentioned in the last lecture. Mostly it was due to in the form of presentations and also an opportunity to ask any questions to clarify. So, the general information that was covered was some context with respect to antennas and batteries. Hopefully, that was something that was helpful for the students, and hope you had a chance to think about some of the points that were mentioned. What are the assumptions in the design of the cell phone and of the antennas, and how that it becomes a safe device to use. Probably an interesting element that helps us understand the system was how a call is made to a mobile phone, basically how a call is made. And I thought I would ask you a question that is connected to this, just to sort of understand the whole process. So, we talked about a landline phone connecting to a cell phone. So, basically there was the landline phone and it went through a certain process and eventually came up to the cell phone. So, this is the last segment of the call being made. Just wanted to ask, how many wireless links are active when one call is made? This is an FDD system. So, there is one link through which the cell phone tower talks to the mobile, and then there is a second link on which the mobile talks to the cell phone. So, there are two wireless links. So, again keep in mind these are some elements that are that makes us understand. Now, the question is, are these two wireless links independent of each other? What I mean by independent is one can be good, the other can be bad. Is that possible in the framework that we have assumed? What do you think? They are different frequencies. That assumption is correct. That's because it's an FDD system. And again, our basic understanding of propagation is that it can be very different for different frequencies. So, these two channels can be assumed to be independent in terms of quality. One may be good, the other may be bad, and even if one of them is bad, your call will not be satisfactory, and eventually the system will drop your call. So, the applied question: so if a mobile were calling a mobile, how many wireless links are? 4. So, there is a higher probability that if you are calling from a mobile to a mobile, one of the links could go bad, and therefore it is a vulnerable channel. The other question, which is when you, I'm sure you probably have seen landline phones, and if you can't hear, you tend to talk louder, right? You shout, you hear people shouting on the landline phone. In a cell phone system, you can hear the other person, but they can't hear you. Will shouting help? Why? So, you can hear them, so which means that one side is fine. They can't hear you, it means the reverse channel is bad. So, in which case shouting is probably not going to help. So, or being surprising, how come I can hear you, how come you can't hear me? Don't be surprised. Sometimes the links can be independent, and therefore the quality is not is something that it's a way the system has been designed. So, there are especially mobile to mobile, 4 links are there. Even if one of them is affected, then we see the effect of that. So, then the rest of the discussion was on aspects of 5G. Again, these are concepts that I am sure post the course, as you look at material, I am sure you will be able to appreciate. One of the elements that I thought I should spend a few minutes, is regarding the computer assignment, and some of the terms which are there, which I hope you would have had a chance to look at, and we will discuss it. If there are any doubts, we will clarify that as we go along. So, the computer assignment was to enable us to simulate using MATLAB or C, C++, whatever you are comfortable with, the bit error rate of a digital communication system. We are looking at bit error rate of QPSK as a modulation scheme that we have used versus EB by N naught. And as I was mentioning to you, EB by N naught is something that is very difficult to specify and implement precisely in a communication system, and maybe a few minutes of explanation will be interesting and helpful. This is information from digital communications. The EB is energy per bit, energy per bit. Okay. So, this is something that you would be able to understand in many different ways. Probably the easiest way is to look at the power of the transmitted signal, PS. So, that is the power of the transmitted signal times the duration of a bit. Power into time gives us energy, TB is the duration of a bit. Okay. Given that it is QPSK, the duration of a bit, duration of a symbol is 2 bits long. So, the bit duration is half of a symbol duration. So, duration of a bit. So, this is the basic definition of energy per bit. Now, the tricky one comes when we start looking at N naught. So, let me ask you to tell me what N naught is. Give me a definition of N naught. It is the power spectral, noise power spectral density, and the units are watts per hertz, noise spectral density. Okay, thank you. That's good. Now comes the intuition part. So, this is in watts per hertz. That's our units, watts per hertz. Now, how do I if I have a certain noise power that I measure in my receiver, how is that related to N naught? And that's a very important element, because N naught, noise spectral density, times the equivalent bandwidth, or the amount of noise that comes in, that is the equivalent bandwidth that refers to the property of the receive filter. This will correspond to my noise power. This is noise power and equivalent bandwidth, and again the definition of equivalent bandwidth, there is a notion of it, but basically think of it as the bandwidth of the receive filter, equivalent bandwidth. Okay. So, with this basic understanding, we now are ready to define our EB by N naught, that is given by PS times TB divided by Pn divided by equivalent bandwidth. Okay. That's a very good equivalent representation, where PS and Pn are things that we can actually measure in a communication system. Okay. Now, this is nothing but PS by Pn times TB times B equivalent. That is just rearranging the terms. Okay. So, I would now like to give you a property of the square root raised cosine filter, which is useful for us to keep in mind, and that would be the understanding that the equivalent bandwidth of a square root raised cosine is approximately 1 over Ts, or the symbol rate. Bandwidth is proportional to the symbol rate when you use the square root raised cosine as your pulse shape at the transmitter and receiver. Okay. So, for us, EB by N naught, that is a quantity that is theoretical but not very practical, can be related to a very practically measurable quantity PS by Pn. Notice when you looked at the simulation, you can actually put the meters, or basically take the magnitude square of the complex numbers and average it. That will give you PS and Pn. Once you have our ability to measure PS and Pn, and this term becomes TB by Ts, right? TB times B equivalent is proportional to 1 over Ts, and this is nothing but 1/2, under the assumption that you are using root raised cosine of the transmitter and receiver. This is approximately 1/2. So, if I were to write it in dB, EB by N naught in dB is PS by Pn in dB, minus 3 dB. That is it. So, you actually have a very precise way of calibrating the amount of noise that you will add and actually get the bit error rate for a specified EB by N naught. This is simple, but it is good to do it once, because only then you feel comfortable saying, okay, EB by N naught is a very N naught particularly is a quantity that is it's a conceptual term, but actually when you want to measure, you want to measure it. And the challenge now becomes measuring the noise power. And that is why we did a basic rearrangement of the simulation system, because the square root trace cosine pulse shaping, that is the receive filter. It is a linear operation. So, I can the signal and noise get added, that is how the channel would work, and noise would get added to the channel and then you pass it through the receive filter. But invoking the property of linearity from signal processing, we can say that, okay, I can move the summation to the right hand side, basically since it is a linear operation. So, which means that each of the branches must go through square root trace cosine pulse shaping. That is what you see here. So, basically I have moved it for the purposes of convenience, moved the receive filter to the right, to the left, and then applied my signal power and noise power, because this is exactly what is coming into my receiver. And because it is a simulation, I can do that. It actually helps me control it. Now, if I want to set different levels of signal to noise ratio, 6 dB or 8 dB or 10 dB, that is controlled by controlling alpha. So, hopefully as you look at it, the complete expression would be alpha squared, because alpha is also present in your expression for the simulation. You would get PS by alpha squared Pn minus 3 dB will be your expression that you should be able to map, and that should match very, very closely as you plot the bit error rate versus the call it PS by Pn if you want, or EB by N naught, whichever one you want. Make sure that you do the correct one. You will get the different simulation graphs, and then you will find that the theoretical graph actually passes through. So, this is what we would like to get. Hopefully, it will be a very interesting and instructive exercise. Okay, so this is pretty much what we covered in the last lecture. Any questions on either the simulation or on the material that was covered in the last class? If no, we move on. Let us pick up where we left off in the last. Yeah. The question is, how does voice over LTE? Voice over LTE is a mechanism which is there in the 4th generation for the carrying of providing the voice service. So, basically the delivery of packets is like any IP application that you have, like WhatsApp or browsing. There is an addressing mechanism which tells you how to route the packets, what the destination is going to be. But the information that going into the packet is very similar to what happens in a conventional circuit switch call. Basically, your voice gets coded into information, which is then encapsulated into the packet and then transmitted through the system. The ability to go from voice over LTE to a conventional voice device. Basically, once it goes into the cellular network and the network recognizes that it is a voice packet and it has to talk to let us say a 2G phone, then it will route it through a gateway which will then convert it into basically a normal voice call and establish a circuit switched path to the user. So, voice over LTE can exist in its own domain, talking to other voice over LTE devices. It can also connect to a PSTN or to a regular 2G phone using appropriate gateway. Okay, let us pick up today's material. Hopefully will be a lot of information, but hopefully this is something that will help you as you read about the material in different contexts. So, 5G, as we mentioned, the goal is to give enough bandwidth so that the user has a perception of infinite capacity. Now, there are lots of projections that are made. It is good to have an idea of how the market is growing and how fast it is growing. Of course, projections of number of cellular users in India have always been smaller than what had happened in reality. But again, it is good for us. So, here is a representation of what the proportions will look like okay, in the year 2019. So, if you look at, there are three colors there, you almost will miss the third one if you do not look for it carefully. It is way at the bottom. All of the voice calls, that voice traffic that we see today, which is a huge amount of traffic in today's cellular networks, is going to be that small line, very narrow line. Okay. What is the rest of it? It is going to be mobile data. And of course, all of the broadband applications that we are talking about are going to be, so it is orders of magnitude more than the voice traffic. The voice traffic is also growing, but the rate at which the mobile data is growing is in several orders of magnitude. Now, they classify it as how much will go on actually handheld devices and how much of it will be on devices like tablets, and but now that's sort of merging. Smartphones are somewhere between a phone and a laptop. So again, it's interesting to know that the data component is very, very strong. So they expect that with respect to 2010, what we achieved in terms of the capacity of the network, there will be approximately 1,000 times increase in terms of capacity needed in the networks. So basically, how do you plan for a 1,000-fold increase in the existing network? The one easy method would be, say, ask for 1,000 times the spectrum. That's not going to be available. So how do you do that within the existing mechanisms? Okay. So here is the way at least the broad idea is going to be. They will ask for 10 times or more bandwidth, more spectrum will be found somewhere in the RF spectrum range. They will create 10 times more cells. Okay. Each time you increase the number of cells, the capacity is going to grow. So if you increase 10 times the number of cells as with respect to today's, your capacity is approximately going to scale by 10. And the last number is very, very important. They want to send 10 times the traffic in per channel as they are sending today, 10 times the traffic, which means that you are asking for very, very high spectral efficiencies. Again, how do we achieve that? A lot of it is going to be the work for the researchers who are going to be working in the area of wireless. So it's interesting to see how the whole system will evolve and why we are why we are studying these topics with interest. Okay. Some elements of 5G, which will be enhancements over 4G. Basically, today we are talking about the speeds which we are in the 10 megabits per second. It will likely to go even higher, 100 megabits per second. They're also talking about 1 gigabit per second on wireless links. It's interesting for us to see how that will be. Today we transmit primarily up to 2 gigahertz, slightly above 2 gigahertz. We are now talking about, because we want 10 times more spectrum, they are looking at the millimeter wave band, 28 gigahertz, 38 gigahertz, 60 gigahertz. Again, these are spectrums, parts of spectrum, RF spectrum, where there is almost no users. So if you go to 60 gigahertz and ask for 1 gigahertz of spectrum, it's probably there, no problem, because but if you ask for such large amounts of spectrum in the lower bands, no way, because so much of users are there. Now, as you go higher in frequencies, your wavelength decreases. Your antennas are proportional to your wavelength, so which means that your size of the antenna keeps getting smaller and smaller. So they are now talking about not MIMO. MIMO would mean about 2 antennas, 4, 6, 8 antennas, 8 at the upper limit. Now they are talking about massive MIMO. 64 antennas, 100 antennas, 100. So basically it will be potentially an array of antennas which can achieve for you orders of more better efficiency than what a normal MIMO system could be. So again, interesting to see how this will play out. Higher order modulation. Today we do QPSK under good channel conditions, 16 QAM, very, very rarely into 64. Now, when they talk about 5G and they talk about very good channel conditions, they are saying why not 256 QAM. So again, the challenges are yet to be seen, but again, all of this is so that we can achieve the type of growth in the data that has been forecast. So it could be voice traffic, small growth, but bulk of the growth happening in the machine to machine and in the data applications that we are seeing. Okay. So those are aspects of 5G. Again, you will see it in a few years, lots of interesting things to work on. But 4G systems are not going to sit and, basically it's not going to be a quantum jump when it comes there, it's going to be a gradual evolution. So today's system, LTE, the version that is going to be deployed in a few years is called release 12. Again, each year there is a release or upgradation of the system. LTE started out in release 8, so basically this is the 5th upgrade that will happen of the LTE system, and here are some thoughts that are already pointing to what it will be in the towards the 5th generation. Okay. So notice higher order modulation will be introduced in LTE up to 256 QAM. They will look at several methods of improved interference management. And one of the ways that it will be done is that through the process of creating these small cells, femtocells, basically large number of small transmitters that are connected, to which users are connected. So not many users are connected directly to the macro tower. So this is called densification of the network. Okay, extreme densification of the network in order to achieve the capacities. We are saying increase the number of cells by a factor of 10. This is one way in which it will happen. Lots of small cells being created. Of course, they will all likely to interfere with each other. So that's why the interference management is very, very important. Now, another very interesting phenomenon that is already being discussed is that there is a macro network, and that has to sort of control how the information flows to the different users. But the actual data which comes to the user, there are two things. One is telling you that, okay, you have some incoming call, or there is a application that wants to connect with you, and then the actual application where the huge amounts of data are transmitted. So there is the notion of control and actual user data. So what they call as dual connectivity is that the macro network will still give you the control information. It will just tell you, okay, you have an incoming call, or you have a data application that wants to connect with your device. So basically it just controls the entire network. But the actual data that flows, this is only a few hundreds of bits, but this will be megabytes of information. That is a thick pipe that comes to you from the small cell that is nearest to you. So today, control and user data come on the same link, but in the future they could be coming from different base stations, and you don't even as a user don't know, but it's a very more efficient way, because this is at a low rate and it has to connect to all the users. This is at a high rate only to a few users, so therefore it makes sense to connect to your nearest base station. Okay. MIMO is today, as we understand it, spatial. It helps you to do spatial resolution of users. I can differentiate between user in this direction to a user in this other direction. They are talking about, this is two-dimensional, XY plane. The evolution of cellular systems, where we also have coverage of users in high-rise buildings, that there is a third dimension. Basically there is X and Y, and then there is a vertical dimension. So the three-dimensional MIMO. So you could have beams in these two directions. You could also have a beam in a different in the Z plane, which gives you additional capacity. Again, that's under consideration. The spectrum that is available today in the 2G and 3G is scattered in different frequency bands, 800 band, 1900 band, and in the 2.3 gigahertz band. The aggregation of carriers. So typically if you want 10 megahertz, you like to have it all 10 megahertz together contiguous. But if you don't have 10 megahertz contiguous, can you aggregate carriers from different frequency bands? And that is also being talked about. Probably the most important and interesting one, along the lines of what we saw in the previous slide, this splitting of the control and data is going to happen in another flavor. That flavor is going to be the incorporation of Wi-Fi. Instead of using the small cells, if you have a Wi-Fi access point, that means the macro network will do the basic control operation, and once it comes to the data transfer, it shifts you over to the Wi-Fi system. So therefore, the Wi-Fi is something that is free of cost. You don't have to pay the cellular network. The cellular network operator is very happy because you have gone off the network and you are taking your megabits per second of data from a different resource. So again, it's a win-win situation. So this is something that is happening. They call it seamless mobility between the cellular network and the Wi-Fi network. Again, there are challenges in terms of mobility, but this is a model that I believe has a lot of merit. I'm sure you will see more of this. Now, engineers are sometimes skeptical. That's good in a good way, you know, because some people have said, look, 5G is too ambitious. You are trying to do too many things, very, very complicated. So there's a group of engineers who have predicted that 5G will die before it even becomes a reality. And here are two reasons why they, again, it's not to say that 5G will not happen. It's an alert saying that, hey, you know, don't think everything is rosy, everything is easy. There are some very significant challenges that are present. Okay? First of the caution notes saying that if you don't address this, 5G will be affected. This is with the aspect of network densification. Now, there is a fundamental assumption that we are making with densification, which says the more cells that you create or more base stations you create, there is more capacity in the network. Okay? Now, what about interference? I am going to generate more interference. There is always the assumption that, you know what, my user is closer to me, so therefore I transmit with less power, and therefore the overall interference to the network is less. But because there is more number of such small cells, interference will grow up to a certain point and then it will saturate. It will not go to the point where you cannot communicate. So basically, it will not become an interference overload onto the system. Yes, interference will be there, but it will saturate and everybody will be happy. More users. And now the caution that is being made is very true, that says that this assumption is true if you allow every user to connect to the base station that is closest to them. Okay, that's the assumption. Now, let's say you have set up your own femto cell, and your neighbor says, hey, can I connect through your femto, and you say no, then what option does your neighbor have? He has to connect to the macro network. So that is a scenario that you may have created a zone in which you have reduced the interference. But if the others cannot connect to the nearest base station, then they are going to create actually more interference, because you are causing interference to your neighbor. Neighbor has to transmit with more power to reach the network. So there is a implicit assumption that there may be some things that we need to look at. The statement which says more cells implies more capacity, because you have not yet addressed the issue of who will be allowed to connect to the nearest base station. So if it were an open access network, anybody can connect to any base station. The fact number one is good. The fact number two is also questioned, because the propagation changes in electromagnetics when what is called the near field. Near field is 10 to 30 meters, and then far field is beyond that. So basically, if you are now very close to your base station, the propagation aspects change. So you cannot always assume your interferer is in the far field, because your interferer may be somebody who is very close to the base station and therefore will cause a lot of interference. So again, the interference elements also need to be looked at, because you now have small cells. So again, engineers are good. This is a problem. It's good for us to study and come up with interesting solutions. The second caution that was given was, in order to do the MIMO systems, the way the 4G systems will have designed it is that they use one analog to digital converter per antenna. Basically, each antenna signal is all the processing is done in the signal in the DSP, and then eventually you convert it into analog, and then each antenna needs a D to A converter. It also needs an A to D. Basically, on the receive side it's an A to D, on the transmit it's a D to A. So now, if you are going to do massive MIMO, and I've got large number of antennas, I have to worry about how many ADCs are going to be running in parallel, how many DACs are going to be running in parallel. And again, you're saying, okay, I want to transmit at very high data rate. let's say you want to transmit at 100 megabits per second, then the caution is that today's ADCs that have to run at such high powers, such high speeds, with a resolution of 9 bits or 12 bits will consume a lot of power. So, for example, today's state of the art A to D converter at 5 gigasamples per second, 9 bits precision actually consumes 500 milliwatts. Okay, that is a lot of power. If you have now 64 of them running in a device, it will be very power hungry. So, again, ADC is going to be a challenge, DAC is going to be a challenge. So, how do you address it? Do not just say my massive MIMO will give me 10 times capacity, you actually have to build devices that actually can meet those requirements. So, caution well taken. I think we want to be realistic and say that okay, maybe massive MIMO will be 16 cross 16, not 256 cross 256. So, a holistic view of 5G. We have to address increased capacity. Okay, that is number one. Densification will happen. How much? We have to see. It has to be done in a controlled manner. Millimeter waves will be introduced because we want more spectrum, and very important, we are looking at a lot of machine type communications which have low latency and high reliability. Why? Because you may have factory automation, you may have vehicle communications also part of this, and therefore these have to be very robust and reliable. So much for cellular. Okay, we have talked almost 3 full lectures on cellular. I think to do justice, we must also look at non-cellular technologies, because until recently, cellular was the dominant technology, and therefore what cellular did, the rest of wireless did, but not so as we go into the future. What is changing? We now hear a lot of discussions around smart cities. It is not a buzzword, because from the point of view of communications, it is a reality, because if you want to introduce any form of intelligence in your healthcare, automotive, in terms of factory, in terms of homes, in terms of water distribution, power distribution, you must have a lot of monitoring. And all of these devices have to send data to some central node, and today they are not wired for that, and therefore the only way they will communicate will be through wireless devices. So, the minute you hear the word smart city, smart community, smart transport, okay, good, there's communication work for communications engineers. So, lots of applications. Technologies that will meet these solutions can be cellular or non-cellular. There's nothing that says that it has to be a cellular technology. Most of these are requiring connected devices. They have to do real-time communications, and again the popular term is Internet of Things, but we look at it as connectivity of these large number of devices is what we are looking at. So, communications issues will be to provide connectivity, reliability, to make sure that you can scale your network, because these will be thousands of devices that are communicating. So, interesting challenges that we have. You may have thought, okay, 2G, 3G, 4G, 5G, okay, how many technologies are there? Now, look at what's there outside of cellular. So, if you were to take only those unlicensed bands, that means you can use the spectrum without paying any fee, 2.4 gigahertz, that is where our Wi-Fi normally works, Wi-Fi 802.11b. Now, notice that there are lots of other technologies in addition to Wi-Fi, Bluetooth. There is a technology called Thread. There are several others. Go to other unlicensed bands. There are technology called LoRa, long range. Sigfox is a signaling technology. There is a technology called weightless. Again, there is a lot of them, and you ask the question, what are they doing? Why did people develop these technologies, and why are they there? What are they used for? So, very interesting to see. This is what these technologies have been developed for. So, if you talk about smart city requirements, you want to control the let us say all the traffic lights. So, you are talking about a large number of devices, and many of them may not have electricity connection. So, which means that they must have good battery life. You are deploying it across the city, so you may want to have long range, but generally these are monitoring devices, so low data rate. So, LoRa is a LoRa is long range, has been developed very precisely for this. It is something for long range, low data rate, and long battery life. It has been designed for. Okay. Okay. So, that is nothing to do with cellular, it has been developed very specifically for this type of application. Now, at the same time the cellular community said, hey, you know, we can actually modify our system to meet the requirements of such a because we already have long range, the only thing is we do not have as much battery life, we can do that. So, they have come up with a something called narrowband IoT, Internet of Things, that is actually a offshoot of LTE, 4G LTE. And there is another proprietary system called Sigfox. It has been designed very specifically for electricity meters, for domestic appliances, basically to monitor it. So, what is the data rate? 100 bits per second. Is there an application for 100 bits per second? You can see that this is one such scenario, and it only requires 100 hertz channel, not asking for megahertz, and it works with very high efficiency. So, if you remember in the first presentation, first session, we talked about a classification of technologies using a 2-axis method. On one axis it was range, on the second axis it was data rate, if you remember the same 2 axes. Now, put all of these new technologies in this one. There we had only cellular and Bluetooth and Wi-Fi, but now let us put the remaining technologies. You can see that there cellular looked like that was not so good, because Wi-Fi and others were much better. But now cellular is sort of the one that everybody else is at lower data rates but lower range, but they have much better battery life. So, that is where the advantage comes. So, if you are talking about an automotive application, maybe cellular is the dotted lines tells you which are the likely technologies that will meet your requirements. Automotive, cellular is probably going to be a good technology, but if you are talking about short range communications, once you enter a certain like a parking lot, then Wi-Fi could equally well be an option. Smart home, which means that it is to do monitoring of the devices in your home, may not require cellular, probably Bluetooth or a system like Zigbee would be done. And there are competitors to Zigbee, as you can see there are several others which are very similar to Zigbee, so you would have to look at some of those. And if you are talking about a smart city, again some set of systems. So, let us look at one of those. There is a technology called weightless. This is a technology that has been specifically optimized for long range. But how does it achieve battery life of 10 years on a system? So, or even for that matter 3 to 5 years is so weightless has got 3 flavors. Again, this is more for concept, the details are just so that you get a feel for. If you are willing to say that some devices are only one-way transmitters, or one way, basically they will receive and not transmit anything, or basically they only do one way transmission. So, very simple, they can last for 10 years as battery life. Now, the same weightless may say that okay, there are it is a two-way device, but not as frequent communication, infrequent communication, then you can get a certain amount of range. And then if you want to have two-way more interaction, then you get lower. So, basically each of these technologies will also give you multiple flavors to then say that okay, you can, when you deploy a network with my technology, then you will find that you have certain advantages with respect to the others. Interesting for us to see some of those elements. Now, most of you are familiar with the Zigbee protocol. It is built on a IEEE standard called 802.15.4. There are other technologies which are built on the same physical and MAC layer. There is a technology called 6LoWPAN, there is another technology called Thread which is built on that. The wireless smart utility network, that is another standard that is of products have been developed primarily for metering infrastructure, electrical power metering. This smart utility network is also designed for street lighting, parking, traffic management. So, basically it is designed for large scale deployments. Z-Wave is a technology like Zigbee. It is meant primarily for turning on devices, turning off, setting locks and things like that, basically for home management. Again, just to give you a flavor, the old ones, old timers, Bluetooth and Wi-Fi, each of them have now got different flavors. So Bluetooth, for example, if you can see, now has a low power mode which is optimized for these applications such as IoT. So basically they call it Bluetooth Smart or Bluetooth low power, which is optimized for that. Classic Bluetooth is itself low power, but now you are talking about something that is even more optimized. Now Wi-Fi, most of us think of it as 802.11b, the one that you see in airports, in shopping malls, in different parts of the academic zone also. But actually Wi-Fi is not a single standard, it is a whole family of standards. Some new standards that you may not have yet heard of, there is a 802.11ah. It's called Halo. Basically low represents that it is in the lower frequencies. Today it's deployed in 2.4. Now they have introduced a version that will operate in unlicensed bands but below 1 gigahertz. That means what used to be 100 meters range will now probably go to 500 or 600 meters. So basically extended range can be achieved compared to the traditional deployments in 2.4 gigahertz. And at the same time it's also low power consumption to compete with Bluetooth. Yesterday there was a question, why do these technologies, all are trying to compete. Basically the market is very attractive and therefore they are looking at it. There is another flavor of Wi-Fi which is operating in the unlicensed, it is in the what is called the white space. White space is current TV channels. TV channels were all given radio spectrum, but most of the TV channels today are either through cable or through satellite, so they do not do terrestrial broadcasting. So therefore those channels are actually not being used for anything else, and they are all in very, very good propagation frequency bands. So white space combined with Wi-Fi, they call it as Wi-Fi, and that's a optimized system to operate in the TV white space. And as we speak, there is also a development of a Wi-Fi system that will touch gigabits per second over the air. So again interesting one. Now interesting to also ask the question, how do these devices avoid interfering with each other? So many of them are all operating in the unlicensed bands. Bluetooth has got a technique called frequency hopping. So every a few milliseconds the Bluetooth network keeps hopping. It hops at the rate of 1600 hops per second. So less than a millisecond is what it stays in each of those frequencies, and it keeps hopping. So the goal is that it keeps hopping frequently enough to avoid any harmful effects of an interference. So let us say there is an interference in one portion of the spectrum, it may hop to a frequency in that where there is a heavy interference, but less than a millisecond it's off to some other frequency which will probably have better channel conditions. But that requires a fair amount of power consumption because it's changing frequencies, and the Bluetooth low energy consumption one has optimized the hopping, basically reduced the hopping rate as well. So interesting ways in which Bluetooth is evolving forward. Bluetooth, as you know, is a technology to connect lots of independent pairs of devices. So what you can create is a lot of parallel connections. But remember, this hopping requires you to be synchronized because you and the device that you are talking to must change frequencies at the same time. So this notion of how the clock is controlled is very, very crucial. If you are interested, you should read up about that. How do you maintain uncoordinated network where every pair of devices knows exactly when to change frequencies? Every pair will hop at a different time. And there are devices that are connected to two networks. How do you hop your frequency to talk to two people at the same time? Very, very interesting problems. It has been solved very elegantly. 802.11, as I mentioned, is not a single standard, it is a whole family of standards. When you get a chance, you can look at this slide and see all the different flavors. We started out with 1 to 2 megabits per second, then went up to 54 megabits per second, 100 megabits per second, and now we are talking about gigabits per second in the same family of evolution. Okay, there are some other technologies which I will just mention. So in case when you are reading it, if you come across, built on the 802.15.4, that is the IEEE specification of the physical layer. On top of that, you can have a standard called Zigbee or Thread. There is also standards called the wireless HART, and these are devices which have very long battery life, and range is limited 10 to 30 meters, but again have got very unique niche applications. Okay. Long range, LR, that acronym always stands for long range wireless personal area networks. So short LR, low rate wireless personal area networks. Okay. LP is low power, and again these are devices that are optimized for very low power. LoRa is long range combined with low power, and Sigfox is actually low rate combined with low power. Now LoRa technology, which is actually designed for long range, how does that achieve low power consumption? And it is interesting for us to sort of get a feel for it. All this is very intuitive. So the y axis tells you how much power consumption. If the triangle becomes narrower, that means it consumes less power, and the green arrow tells you how much delay is likely to be for data that is being sent by that particular mode. So class A is very low power but may incur large latency. Class C on the other hand is the one that is very low latency but will require more power, but still overall it is still low power, but there is still optimization within that. How does that optimization occur? So the optimization basically says that you transmit and then you shut off everything. You periodically wake up only twice to see if there is any downlink transmission. Okay. If there is no transmission, you go back into what is called sleep mode and you shut off all other devices. So this basically says that if you have to communicate with this particular device, you can only communicate when the receiver wakes up. So which means that there could be a lot of delay in communicating, delay of the order of milliseconds. Okay. Now class B says I will have more times when I wake up. So which means that you will consume a little bit more power, the latency reduces a little bit, and then there is a class C which the receiver says you can talk to me anytime, I will be awake, I will wake up and communicate. So again you can see that how the optimizations occur for the different systems, how Bluetooth avoids efficiency, how LoRa reduces power, how the weightless technology reduces power. So again all of these are optimizations that you see happening in the wireless technology for the specific application that we are looking at. So this is the non-cellular view of the world. They say cellular always draws cellular big and everybody else small, but here is our view of the things. They say that the wireless personal area networks, wireless PAN and wireless LAN, that is going to be the dominant technology. That is what they feel. Okay. So they say that okay, billions of things are going to be connected, much more than number of human people, so therefore that is going to be our technology. And of course low power is very important, that is going to be a huge part of the market. Where is cellular? Oh, by the way, we will give them a small portion, so there is this portion. So again this is a slightly different perspective on how the wireless market will be. They are looking at connectivity of devices. They are not talking about total communications or profit or total data. They are saying that when it comes to connecting devices, it is going to be the non-cellular technologies that will be dominant, but final decision the market will decide which will be the winner. Let me make a couple of comments with regard to the upcoming classes. There will not be a lecture on 17.1, we will have a makeup lecture. So basically next Tuesday there will not be a lecture. I just wanted to inform you regarding that. But there will be an uploaded reading assignment and a written assignment. And the TAs will be available during the Tuesday lecture hour, but for a discussion, if you have doubts on the computer assignment or on the written assignment, they will be available to answer any questions, and we will let you know through Moodle which room this discussion will take place. So in case somebody is having difficulty accessing Moodle, please do stay back, because we need to make sure that everybody has access to Moodle so that we can send this information to you in a reliable manner. Okay. And regarding the makeup lecture also, we will announce well ahead of time when the makeup lecture will happen, but the makeup lecture will take place here in the studio. And feel free to stay back after class, after lecture. A few students do, if you have any doubts to clarify, and if there are questions that I believe will be of benefit to the entire class, I will take it up and I will also answer those questions, repeat the answers in the next lecture that is present. So let me pause for a moment. If you have any questions on what we have talked about. Today we have talked about a lot of non-cellular technologies and what they are doing. And any questions on what we have covered today? So the question is, what is the role for satellite? The element to keep in mind is any satellite link will have longer transmission delays compared to a terrestrial system. And particularly if you are talking about a medium earth orbit or a geostationary orbit, the transmit power required is going to be more. So the satellite based communications are okay where there is no form of terrestrial coverage, but when terrestrial coverage is present, satellite communications always becomes a more expensive technology, because you need more power, you need to have more expensive equipment. When it comes to connecting devices, satellite will definitely not be an option, because the power required will not be anywhere close to what these low optimized power systems will achieve. So satellite has got a role, but it's only where there is no coverage today, terrestrial coverage today. If you're over the ocean, there's no coverage, satellite phone is the best way to communicate. But but if you're in metro, definitely satellite would not be a good option, not for voice, not for machine communications. Let me just show you one slide and then I will pick it up from there. Basically, when we talk about smart X, probably the most common thing that from a communications perspective that will happen and have a huge impact is adding communications to the electricity grid. I'll just explain in 1 minute what this means, and then we close with that. So today the way the electricity works is that you generate, you have a generation point, then there is a transmission point, typically at some high voltage, 110 kV or some, and then there is a distribution system. IIT has got a distribution system which is on a 11 kV ring, and then you have your customers like your hostels or residences, where it's converted from 11 kV down to 440 volts, and then you supply the customer. The future, when you start doing things, the first thing happens is, let's say the customer is generating renewable energy and wants to feed it to the grid. So the customer should be able to tell the network how much they are producing and when they are producing, and they are going to be feeding it. So the flow of power is no longer one directional, it's now bidirectional. So basically there is power flow from the customer onto the grid. Now you have to measure how much power the customer is feeding, so that is the metering part. You must also know when the customer is going to ask for power. So basically consumption, that information is through smart meters and through smart appliances. Now you as a customer can no longer have to buy only from one power source. You can buy power from, in the future, probably from your neighboring state or from a third party who is willing to supply. So basically there's going to be dynamic pricing, just like stocks. Everybody is going to be putting up their prices, and then you optimize and say, okay, I'm going to take it at this time. So what we see today as the grid is completely changing because of the introduction of renewables, because of introduction of the dynamic pricing and the ability to buy power not only from your local distribution agency, but from anywhere basically from a variety of other sources. So this is something which we believe will be a good model for a smart grid and what type of communications will be needed in a smart grid type. So we'll just spend a couple of minutes trying to answer that question, and then bring the whole discussion to a close at the start of the next lecture. Thank you.